Good morning. So first of all, I would like to thank the organizers for the invitation. So my talk will be a bit different than the talks we had before. I would like to highlight open questions that we have in common, organization is what we know and what has been tested. And then I will tell you what are those questions where you need to provide something. So let me start with this page. With this very known kind of time, that where we come from, where are we going? So that's the title of this painting, which if you want, in cosmology, that would apply with 3 questions. How was the universe created? What is the universe made of? What is the ultimate value of the universe? So these are 3 questions that we try to address within the, let's say, lambda CDA model, which is a phenomenological model based on a robust theory of general relativity and enriched with dark matter, usually called dark matter, no interactions, dark energy, which means the cosmological constant, that's it, and also a mechanism for a very early, fast expanding of the universe, which is called matter inflation. So let me take one by one these kinds of ingredients of this components model, and then I will tell you the open questions of the crisis that is the phenomenological model face. So I would like first of all to take the test of general relativity, and I will concentrate on the test that we have made on the third observing ground of the light of the collaboration. The current one is going to finish on the 18th of November. But the data are still not public, apart from the few results highlighted. So, what you do, you have a lessons of the compact binary system, then your data will be waveform. You find from your data what is the best fitting waveform. You're going to subtract that, and what remains is that noise. Any kind of post-Newtonian coefficients which you find they are consistent with the predictions of GR. Then, if you have the GR is correct, you're going to have the Mohr conjecture, which means that when you go to calculate what would be the quadrupole moments of the binary system, then they will be given by, you will get some values which are fixed, and they depend only on 2 parameters, what is the mass of the spin. And that's exactly what we found. Now, you try to test whether you are going to have any kind of deviation of the standard dispersion relation. So you have this phenomenological term, which usually we put there. The values of the capital A and the small alpha depends on the different models, and then constraints have been put. No evidence of dispersion relation. If you have a model, a theory, which is beyond GR, you can have up to 6 polarization modes. A priori, you need 6 detectors to find it, so we don't have 6 detectors. But we came up with a Bayesian method to study for that. They does not find any evidence for non-GR modes. If you are beyond GR, then we can have some very compact objects which do not have horizon, would be more massive than neutron star without horizon. Then in that case, what may happen is you have that the ingoing gravitational wave is going to reflect on the object itself, and you are going to have a sequence of this kind of wave packets, which depends on the frequency, and they decrease as time goes on. Nothing like that, this kind of ecos, post-model ecos that have been suggested in this model is second half. There is the stronger bound of the possible non-zero mass of the capital, 10 to the minus 23 electron-volts square. And then the relative black holes, you know, the system, you have the coalesced black holes, then the system is going to relax to a new black hole with a smaller mass. And what we have found that in order to that, it releases gravitational waves on quasi-normal modes, which depends exactly on the frequencies and the damping times that you know from GR theory. So no deviation from GR. Now, the most amazing result that found and was fast, that's why the fourth observing ground that came out in the physical calculators very recently, was from the gravitational wave merger that was found on the 14th of January 2025. It's like the first detection two black holes in about 114 or 12 billion light years back of about 30 solar masses. But in these 10 years of lapse, we had much better kind of the sensitivity of our parameters. So the first detection had a signal to noise ratio of about 35, now it's about 80. So like that, we were able to test both the Kerr nature of the black holes and the Hawking area law. In other words, the remnant event horizon area was found for a very high credibility that is bigger than the initial one, which is in agreement with Hawking. And again, there was a confirmation of the Kerr spectrum of the remnant black hole. So that's one of the very few results that have been published and published from the last observing time. So nothing beyond GR so far. Now the question is however valid general relativity in all scales? And you have another kind of let's say number of theories which are modeled. The majority are phenomenological theories. Some of them they can be motivated from a fundamental theory which goes beyond GR. So how can we test it? The approach actually is that you have to link data from cosmic microwave background, from large-scale structure, from gravitational waves, with classical tests of parameterized Newtonian. And probably big surveys of galaxies, for instance, the Euclid that we have now, or the Special Very Radio Telescope, could be able to study perturbation modes very close to the Hubble scale. So we'll be able to test validity of these theories for large scales. And that's what this has been proposed, but of course we need more data in order to do that. And of course we know that when we go to very high energy scales, then we have similarities. And the point here is so we know that at some point we have to go beyond zero. The second ingredient is that usually has been obtained like contact matter no interactions, even though there are models of all that matter interact with that matter in general. The data that we have about that comes from rotation curves, gravitational lensing, objects, clusters, or the CMB. Now, a way that you can see that is that if light traces matter, if you see that you have a cluster, a galaxy, whatever, and you find the light, and therefore how massive it is, then it's not sufficient mass in order for this thing to be bounced. So there is much that we cannot see. So there is a number of suggestions that we made there. At first, there was Micro's suggestion of modifying Newtonian elements, a beautiful but purely empirical law, passing successfully. Once you try to promote that into relativistic theory or spectrum science, the theory is tensor vector scalar. It's my best theory that I have seen. So the problem is that it has a couple of free parameters, and you cannot fix the same value of these free parameters to have flat rotation curves and gravitational lens. So then there is a number of dark matter candidates, and the ones that have been they are more, let's say, fashionable in some case, is primordial black holes and action-like particles. Primordial black holes, why? First of all, we have seen black holes, so they could be primordial black holes. There is a large variety of mechanisms that can imply the existence of primordial black holes. And then you put constraints on the fraction of primordial black holes to the dark matter. So there is a beautiful kind of review articles, in particular by Bernard Carr et al. And more recently, we put a new constraint from the gravitational wave data onto the fraction of black holes, the primordial black holes that could be the dark matter of the universe. Another thing is action-like particles. So the idea here is that you might have like a pseudo-scalar particle, like a QCD behind or something. Now, if you have such an object in a very dense system, like in neutron stars, then you have correction to the action potential. So if you have two neutron stars with this scalar field, then you might have a new kind of field. So when they coalesce, you are going to have a contribution to the gravitational wave radiation. So instead of having just the GR part, you are going to have an action kind of contribution, and then you can put constraints to the mass. It should be smaller than to the mass of smaller than 10 to the minus 11 electron volt for a decay constant of about, if I'm not wrong, 10 to the 18 to the 16 GeV. That will be only faster neutron star binary neutron star directional tuning. So constraints can be put in this particle to that full failure or that. The whole kind of there is a large number of papers and it increased daily about the contribution of primordial metals to the environment. And the simplest way that we can find it, if today we find the gravitational data subsolar mass, then we know that should be a thing of the planet. Now, that happens. So we have observations coming from type 1 supernova, from the cosmic microwave background. You see the peak, the first of the peak, it appears, it arrives at the value exactly that tells us that the universe should be flat. Okay, so at this lambda, at this L of about 200, baryon acoustic oscillations or with gravitational lens. And there is again a number of models that have been suggested that to play this role of the accelerated expansion in the unity. A cosmological constant, the identity reaction, modified Magner models, for instance, with tensors. So you have this phi, which is a time-varying scalar field that slowly goes down to its potential. We could have K essence, which here you have the action with this model. You have a scalar field with a non-linear kinetic energy. It has negative, we have like negative pressure. Here you don't need to have potential. These are models that have been suggested. I'm not saying how natural they are or not. A couple dark energy matter, for instance, perfect chameleon mechanism. These are models that have been proposed to particle physics. Unified model with dark energy and dark matter. And then you could have modified gravity models, all this kind of plethora of vector-part gravity models. You can have higher correction terms here, or you can have any kind of, these are completely phenomenological models that have been built, or you could have models with extra ranges. Okay, this is the magic in the bulk, and this is the magic on the brain. So you have a plethora of models that have been suggested to explain the issue of the dark energy. Now, you have as well, I said that the model is also enriched by a mechanism of early accelerated expansion, which has three equivalent kind of definitions. Either you have decreasing the horizon length, or you have the second kind derivative of the scale factor to be negative or positive, or you have this kind of as the equation of state of a scalar field. Now, here I would like to specify that the one of the let's say of the successes of this model is that once you go to solve Einstein's spectral equation, you need to give the initial conditions. There could be adiabatic or isothermal initial condition. It seems to be that the model is in agreement with adiabaticity, the CMB. This can be found in the case that you have single peak deflation, okay? However, if you have multiple peak deflation that has been also used in the literature, then you will not want to have the peak exactly at that position. And the CMB, I want to emphasize that, has not proved the validity of deflation. It has proven the consistency of adiabatic Listen condition. An example would be single peak scalar deflation. However, there are again a number of open questions here. What is the initial conditions that you need for this inflation to take care? The onset of inflation, as we call it. It has been, we don't know any scalar field that could place the lower atom. It has been suggested Higgs inflation, by these people here. However, in order for this Higgs equation to work, you need this particular value of the coupling of the Higgs. So I'm not sure how this one is really very natural. And again, there is this constructing problem. Now, from my point of view, the mechanism of initial expansion of the universe has been, it is valid, but I do not think that this is the result of a scalar field. I think that this is the result of the quantum gravity kind of correction in the system. So there is a number of alternatives that have been suggested. String gas cosmology, which is based on the coupling a gas of close string bundle to a background space-time geometry. Now, this has been then upgraded to a brane gas cosmology, once it has been shown that there can be branes of very energies, depending on the string theory you want to adopt. A matter bounce that has been suggested, and this can be realized in various models, or a kind of cyclic universe. You have a collision of two branes, and this again is a model that can be accommodated in a number of different scenarios. So these are alternatives to the standard inflationary scenario, and more and more people will go with the energy. That's because the inflation to a scenario is not necessarily success. Also, there are many models where you cannot accommodate the conditions for a successful inflation within a kind of gravity theory. Now, then I go back to the structure I had before. How was created the universe? So you couldn't equivalently ask how did the universe come into being? What was there before the Big Bang? Is the similarity real or absolutely is it complete? And I think that these questions have to be faced within the context of the quantum mechanics. So then we proposed years back that I can write down the wave function of the universe, okay, this psi here, which depends on the space of both geometrics and the field configuration, is going to satisfy a Wheeler-DeWitt equation. So then you have to solve it, and to solve it, you have to determine what will be the boundary condition. And there are two types of boundary conditions that have been suggested. You take either the Hartle-Folken, no boundary proposal, or the Villani tunneling out of nothing proposal. Okay? So in the first case, here is the wave function of the universe, which is a Euclidean path integral over all these compact geometries G, okay, which is bounded in by three geometry H with this field configuration. So instead of having the Big Bang, you have this no boundary. Space and time should have no boundary in the path. Or you might have the Vilenkin tunneling out of nothing proposal. So this you integrate over the Lorentzian histories, and then you are going to interpolate from this vanishing geometry and this H and 5, which lies to the past. So these are the two. There is a big debate, which is the correct one. There are some comments that in the Vilenkin proposal we might not get the entirety of them, but I think it's worth noting. Now, so if there is a second question of what the universe is made of, so unfortunately, the main part of the component universe is still in the dark set, but dark energy or dark matter, and we don't know. And here we can find proposals, but there's no consensus of what is the universe. What is the ultimate fate of the universe? Actually, this depends on what is dark energy. So it might go to a big crunch, it might continue to expand forever, it might go to a big chin, which is the maximum possible entropy that the universe can reach. So the answer to this question depends on what is dark energy. Now, and then in addition, there is a number of crises that we call open questions which exist that is a challenge for the validity of the components that they want. One is what is the current expansion of the universe? In other words, what is the value of the Hubble constant? And here I give you a compilation of a very recent paper from the Cosmology network, where they took all possible data which exists and the possible values of H naught. So the idea in two words is that there is a discrepancy in the value of the rate of the expansion of the universe today if you take late or early kind of data. If you take the sound horizon angular scales, the CMB, and baryon acoustic oscillation, the value is about 67 kilometers per second per megapascal. If you take the luminosity of a supernova type of 1, then you get a value of about 73. And you might have there is a complete independent estimation of the rate of function of gravitational waves, which goes between the two. So the resolution is not so. So there is a large number of proposals that has been found in the literature, which try to address this question. Early dark energy, late dark energy, rapid transmission in late units, interacting dark matter with dark energy, modified gravity, exotic scenarios and non-standard dark matter, extra relativistic species and neutrino physics, local void hypothesis, primordial magnetic fields, inflation in models with no standard heating, very fundamental constants, local physics solutions, and systematic acceptance and calibration. In this paper that I put here is a white paper of, I don't know, 80 pages or something like that. You find the study of all these possible kind of proposals. There is no consensus. They have plus and cons. So there's no consensus on it. So there is a challenge to the Lambda-CDM concordance model. In other words, how to reconcile local late-time measurements with global early-time measurements. In the first case, you can say that there are some astrophysical systematics. I'm not involved with any of this data, so I'm just telling you what exists in the literature. So, but these astrophysical systematics are not sufficient in order to explain these discrepancies. And then there is this global constraints which depend on the model that we're going to assume. Now, the gravitational waves give an independent approach because it's not going to be plagued by electromagnetic kind of systematics uncertainties, but still there is no constraint. Now, there's another crisis in the concordance Lambda-CDM model. This sigma F parameter. So this is a parameter that measures the clustering of matter in the unit. And again, here, the value that you get when you get the cosmic microwave background measurement and local probes like we collect galaxy cluster abundant studies, the value is not the same. So again, different data which depends on early or late from local or global kind of studies do not give the same value. Moreover, there is a number of other issues in the Lambda-CDM model. Anomalies and challenges which come from confrontation with the Lambda-CDM and observational data. Excess length in amplitude in the black data and deviation from the Lambda-CDM predictions. Slight preference for a closed universe within the Lambda-CDM. Low quadruple moment and its alignment with the octopole. Hemispherical asymmetry and the CMB cold spot. This is it. So the conclusion of that is that the Lambda-CDM model has been constructed by hand to explain the data, and now it seems to have discrepancies and anomalies when we try to fix all the parameters of this model from the data. And there's something I would like to specify here. I keep saying that given that you have the data, the raw data are useless. You have to put them within a model in order to extend it, to sign it. And then what you do is a consistent step. You put a model, you find the model, and it fixes its parameters. Now, seems to be here that by fixing its parameters, you can. So in my mind, the Lambda-CDM model is it has advantages. Well, it's not by mind, but it's an element. Now, and then you get to other questions. What is the state of the universe? We do know that we can study from the data the local geometry, which means the special temperature. And we know that, as I told you before, that depending what is the geometry of the universe, you will have differences in the mass of the temperature and isotopes in the sky. Okay? So now we have an agreement, more or less, that the universe should be flat. This is the local geometry. What about the global geometry, the topology of the universe? Simply connected space, multiply connected space, finite or infinite wormholes. This is all. In about, if I'm not, I think I know that more than 10, 15 years ago, there was work by Luminet in France, who was trying to study the local geometry, the topology of the universe from the CMB. I've not seen any more recent paper to that, but I'm very skeptical again for the validity of the studies, exactly for what I thought. You put them in the framework of what you studied, so if you put the framework of it is none of these kinds of topology. I don't see how they're going to test it out. So anyway, this is an open question. Yeah. Then I would like to mention other questions, the baryon symmetry of the universe and the baryogenesis, because I know that the people are going to mention here, and that's another open question. We have two completely different sets of data from the power spectrum of the CMB and from the Big Bang nucleosynthesis that tell us that we think that there is a baryon symmetry. Okay, so this number here, which gives you the number density of baryons to the number density of photons from two sets of data which are completely different, it gives almost the same number, 10 to the minus 10. Now, many years back, in 1967, Sakharov had given the criteria that the theorem must fulfill in order to explain the baryon symmetry of the universe. The theorists should have baryon-violating interactions. The interactions should violate both charge and charge parity conjugation. The process of the net baryon number generation should have a degree of irreversibility, which is the result of autothermal equilibrium dynamics. So within this kind of framework, there have been different kinds of scenarios that have been proposed and have been studied in the literature, which try to explain why it's not undermined in the universe. I'm going just to highlight a few of them. Baryogenesis through the decay of a heavy particle. So this is based on an idea of out-of-equilibrium violating decay of the ground unified theory particle. However, here there are some constraints which come basically from the very strong experimental limit on the lifetime of the probe. Baryogenesis at the electron phase transition is another mechanism that has been studied a lot. And here, this baryon asymmetry universe is going to be generated by baryon and electron violating spiral interactions at about 140 GeV. And this, you need a first order phase transition. Okay? In order to be able to accommodate such a scenario, you have to go beyond standard model. So, for instance, in the supersymmetric standard model, very standard extensions would probably accommodate that. Baryogenesis through leptogenesis. Okay, so again, you have a lepton number evaluating decay of heavy Majorana neutrinos, and then this decay is going to lead to net lepton asymmetry, which then is going to be converted to B plus and violating process. So there are many other mechanisms that have been studied. I just summarized the three one, which I think are quite well studied in the literature, pretty old as you can see. Now, why do we live in 3 plus 1 dimensions? So that's another open question. And there are models, for instance, within string theory and as I mentioned, where you need such a dynamic, otherwise the theory itself is not consistent. I think that this theory is this issue might be seen as a pathology, but I don't know. I'm not in favor or against the string theory kind of approach. At some point, just to play, we suggested a mechanism where you could have how you could have interaction of brains of different nationality and they live in the vacuum, and then how they decay and they become just three-dimensional brains and one-dimensional brains that are in this fundamental space. That's what I but another open question for that. So my conclusion is, despite the big progress with physics cosmology, in particular, through a prefora or other precise, realistic, observational and experimental tests, it's more progress that is needed. Not only because there are some fundamental questions which we don't know, like the dark structure of the universe, but as well because we see this kind of challenges that the phenomenological concordance language in the end is facing. So I think that more data as we go along we come, from gravitational waves with current the thermometers, with the one VISA in space, with the third generation of thermometers, but as well with many astrophysical data. For instance, the James Webb Space Telescope, the Fermi Gamma Ray Space Telescope, the Looking Observatory, so on and so forth. And a number of astrophysical kind of information that we have. But coming back to the audience here, it's more on the mathematical side. I think that to make further progress with some of the fundamental questions, I think that more kind of discussion with mathematicians is needed because probably extra tools we need than the ones that we have now. Thank you very much.